Essentially, what happened before the Big Bang, right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that. Because we can see it as we look out into the sky, our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. What existed before the Big Bang? Scientists have always faced difficulty in answering this question. However, it now appears that they have the solution. But it has left scientists shocked, as Brian Cox revealed that something terrifying existed before the Big Bang. So, the idea is, the universe was, in a sense, cold and empty and expanded extremely fast, and that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which were made. That's what we call the Big Bang. So what existed before the Big Bang? Why has it left scientists terrified? Let's find out. And that theory has a kind of extension called eternal inflation, which is that the inflation essentially goes on forever, and it just stops in little patches. So, you imagine the stretch, the fabric of the universe, space-time, stretch, 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 and then it slows down and stops in little patches. And each one of those patches is basically a Big Bang and a universe, of which ours is one. So, you end up with this sort of picture of an infinite fractal universe of, basically, an infinite number of Big Bangs, and that's called the inflationary multiverse. In the vast cosmos, the idea of absolute nothingness seems theoretical rather than real. Even if all energy were removed from the universe, it wouldn't be truly empty. Currently, the universe is full of matter, radiation, antimatter, neutrinos, dark matter, and dark energy. Even without energy, the universe still creates new forms of energy. This phenomenon confuses us. It seems the universe doesn't understand our concept of complete emptiness. If we removed all energy, leaving a void, one might expect the universe to reach absolute zero with no particles. Yet that's not the case. Even in an empty universe, its expansion would still produce radiation. This extends far into the future, or even back to the time before the hot Big Bang. The universe, it appears, never truly becomes void. Given all of this, is it plausible that the universe originated from nothing? We can be certain that something always persists, even if particles, antiparticles, photons, and quanta are removed. Empty space remains. If we move away from any mass or energy sources, clear the space of external electric, magnetic, and gravitational fields, and prevent photons or gravitational waves from entering, a kind of physical emptiness still exists. In this space, quantum fields endure, and the fundamental constants and laws of physics endure. There is an inherent, finite, positive, and non-zero value of zero-point energy in that space. Within our universe, this represents the closest thing to nothing. While you might envision an even more nothing-like state, it lacks physical reality. No experiment can replicate such a condition. By adhering to scientific principles, we acknowledge that something always exists because true nothingness cannot coexist in our universe. However, science has not provided an answer to the question of why. Presently, our universe appears far from empty. It's teeming with stars, gas, dust, galaxies, quasars, cosmic rays, and radiation from both starlight and the remnants of the Big Bang. With improved observational tools, we could potentially detect additional signals that we anticipate are present. This encompasses gravitational waves generated by any mass moving through a changing gravitational field, the mysterious signals from the constituents of dark matter, and a broader perspective on black holes, both active and dormant, aside from those emitting the most radiation. Everything we observe occurs in a universe that isn't static, but is continuously changing. From a physical standpoint, it's intriguing to comprehend the evolution of our universe on a grand scale. The fabric of our universe, known as space-time, is expanding. This implies that if you position 2 points far apart in your space-time, the proper distance between those 2 points, the time it takes for light to traverse between them, and the wavelength of the light traveling from one point to the other all increase over time. The universe isn't just getting bigger, it's also getting colder. As it expands, light stretches to longer wavelengths. It moves toward lower energies and cooler temperatures. The universe was hotter in the past and will become even colder in the future. During this process, objects with mass or energy in the universe attract each other, forming clusters and creating a vast cosmic network. What would remain if everything, matter, radiation, and energy, were eliminated in some way? Essentially, you'd have empty space itself, still expanding, still governed by the laws of physics, and still influenced by quantum fields that fill the universe. This is the closest physical approximation to true nothingness. Yet, it still adheres to specific physical principles. To a physicist, in this reality, removing anything else would create an unrealistic state that no longer reflects the cosmos we inhabit. This suggests that dark energy, as we currently understand it, would still be present in this hypothetical universe devoid of matter. In essence, if every quantum field in the universe was set to its lowest energy state, we would arrive at the zero-point energy of space, where no additional energy could be extracted for mechanical work. In a universe containing dark energy, a cosmological constant, or the zero-point energy of quantum fields, it's plausible that the zero-point energy wouldn't be truly zero. As the universe continues to expand and cool, there will come a time in the distant future when radiation becomes the dominant component, surpassing other forms of matter and radiation, leaving dark energy as the primary influence. However, there is also a time in the history of the universe when something other than matter and radiation ruled, not in the future, but in the distant past. During cosmic inflation, prior to the hot Big Bang, our universe underwent extremely rapid and constant expansion. Instead of being dominated by matter and radiation, the cosmos was controlled by the field energy of inflation, akin to today's dark energy, but much more potent and expanding at a significantly faster pace. If eternal inflation is accurate, but time remains finite, where might the universe have originated? There must have been a beginning, correct? To address this question thoroughly, let's unravel 3 commonly conflated concepts and discuss each, individually. The hot Big Bang in relation to our universe, the theory of cosmic or cosmological inflation and its role in preceding and preparing for the Big Bang, and the issue of an ultimate beginning or origin for our universe, and why both inflation and the original concept of the Big Bang might not offer a satisfactory solution to this question. In the early 20th century, when 4 important pieces of information came together, there was a significant synthesis. A breakthrough by Alexander Friedmann in Einstein's general relativity showed that a universe filled uniformly with any form of matter and energy cannot remain static, but must either expand or contract. The rate of this expansion or contraction depends on the overall energy density of space. Henrietta Leavitt's observational work established a connection between the period of brightness and dimness of variable stars and their inherent brightness, known as the period luminosity relation. Observations by Vesto Slipher measuring the shift in light, either red-shifted or blue-shifted, from our solar system's perspective in spiral and elliptical nebulae, which were later identified as galaxies, indicated that these galaxies were moving away from us at incredibly high speeds. Edwin Hubble, alongside Milton Humason, identified similar types of variable stars to those found by Henrietta Leavitt in spiral and elliptical nebulae. This enabled them to gauge the distances to these galaxies and confirmed they were beyond our own. These findings, combined with other data, led to the concept of the universe expanding. If the universe expands, it suggests that over time, space itself stretches, causing the matter within it to become less dense. As space expands, radiation, like light waves, not only becomes less concentrated, but also stretches, leading to the universe cooling. If we rewind the clock, the opposite would occur to matter and radiation in the universe in earlier times when the universe was younger. It was denser and hotter. If we rewind further, all matter and radiation would have been squeezed into a smaller space, increasing the density of the universe. The light, which stretched due to cosmic expansion when we reverse time, would have had a shorter wavelength, resulting in hotter temperatures. If you envision going back as far as physics permits, you'd reach a singular state where all matter and radiation existed within a single point of infinite density and temperature. The initial idea of the Big Bang theory resulted in the formation of 5 key expectations regarding the early universe's hot and dense conditions. These forecasts became the foundation of the Big Bang theory. The universe ought to demonstrate expansion as indicated by a distinct redshift distance relationship among extragalactic objects. Initially, the universe should have been relatively uniform, with structures like stars, galaxies, and clusters of galaxies gradually forming and evolving over time. In the past, the universe was hotter, preventing the formation of stable neutral atoms. This prediction led to the discovery of the cosmic microwave background, which is observable today. In the initial stages of the universe, when it was extremely hot, atomic nuclei couldn't form stably. This led to the creation of light, elements such as hydrogen, helium, lithium, and their isotopes. The universe was so hot that neutrinos played a significant role. Recently, this prediction was confirmed, indicating that cosmic neutrinos should have detectable effects on both the large-scale structure and the leftover radiation from the Big Bang. With strong observational evidence supporting these predictions, the Big Bang theory has remained uncontested as the primary explanation for the early universe since the mid-1960s, coinciding with the discovery of the cosmic microwave background. As evidence supporting the hot Big Bang theory grew in the 1960s and 1970s, certain challenges surfaced that the Big Bang alone couldn't resolve. Several observations contradicted the concept of the universe originating from a singular state of incredibly high temperatures and density. Among these difficulties, 3 stand out: the horizon problem, the flatness problem, and the monopole, or ancient relic problem. The horizon problem: when we observe different directions, the universe seems to possess uniform temperatures and density throughout. However, since the onset of the hot Big Bang, these regions have never had the opportunity to communicate, exchange information, or achieve thermal equilibrium with one another. This raises the question, how did they evolve? To exhibit uniform temperature and conditions across the board? The flatness problem: there is always a tug-of-war between the initial expansion, which is tearing things apart, and the gravitational forces, which are attempting to bring them back together in an expanding universe. Remarkably, in our universe, these opposing forces appear to be perfectly balanced, resulting in a spatially flat universe. The question arises, why did our universe come into existence with these particular characteristics? The monopole, or ancient relic problem: if the universe underwent extreme temperatures and energy conditions in its early stages, why do we not observe any exotic remnants, such as right-handed neutrinos and magnetic monopoles? Theoretically, these particles should be detectable and still present today. Rather than just taking these conditions as how the universe came to be, which contradicts the scientific method, scientists are looking for a mechanism that would establish and arrange these initial conditions. Alan Guth introduced a solution to these cosmological mysteries in 1980 with a groundbreaking paper. He suggested that an early phase of rapid and continuous expansion, where the universe's energy wasn't spread among matter and radiation particles, but was an intrinsic part of space itself via a field or another mechanism, could solve all 3 issues. Regarding the horizon problem, the uniformity of temperature and density throughout the universe is attributed to the past interconnectedness of everything. This connection stretched during the early expansion phase, called inflation, resulting in the current conditions observed. For the flatness problem, inflation expanded the universe so much that regardless of its initial state, the visible part now appears uniformly flat. As for the monopole problem, the absence of ancient remnants is explained by inflation preventing the universe from reaching excessively high energies or temperatures. The maximum temperature reached after inflation avoids the formation of these remnants. In the 1980s, inflation theory made precise and testable forecasts about the beginnings of cosmic structure that should be detectable in both the cosmic microwave background and the large-scale layout of the universe. These forecasts, crafted decades ago, have been validated by observations spanning from the 1990s to the present day, encompassing an almost, though not entirely, scale-invariant spectrum of imperfections, variations in density and temperature, density irregularities that are entirely adiabatic and not at all isocurvature in essence, fluctuations on scales larger than what a signal traveling at the speed of light in an expanding universe could generate, and a maximum temperature limit for the universe during the hot Big Bang, notably smaller than the Planck scale. Because inflation involves a rapid expansion of space rather than culminating in a singularity like the original model for the Big Bang, it presents an alternative depiction of the beginning. Instead of time and space gradually emerging from a single state, inflation proposes a rapid expansion leading to the Big Bang. This raises a fundamental question about the actual beginning of the universe, if such a notion even makes sense. Within the framework of the hot Big Bang, without inflation, we could trace back and reach a singular state where the universe's size approaches zero in a finite amount of time.